You may have heard the phrase, energy can neither be created nor destroyed. The line goes on beyond this, though. It continues. Rather, it can only be transformed or transferred from one form to another. It is for this reason that a perpetual motion machine cannot exist. This all happens because of the first law of thermodynamics, which is the law of conservation of energy. So, when we are looking at any system, its energy and mass must be exchanged, released, converted, basically conserved in some way, shape, or form. An example of such a system can be found in radioactivity. Radioactivity was discovered in 1896. It was first observed by Henry Becquerel in uranium, and later by Marie Curie in thorium. A handful of years later, in 1899, Ernest Rutherford separated these radioactive emissions into two types, alpha and beta. It is this beta, now known as beta minus decay, that we want to look more into. Because there for a while, it seemed almost as if it was violating the law of conservation of energy. Attention was drawn to this along with a potential solution by theoretical physicist Wolfgang Pauli in the year 1930. He writes it in a letter that begins with, "Dear radioactive ladies and gentlemen." In this letter, he details that in the beta decay process, something with mass and energy seemed to be missing from the particles detected after the decay occurred. He reasoned that something was there and that we were just unable to detect it. He called it a neutron, but we now know it as a neutrino. Before we move on, let's ask the question, what is beta decay? Now, in nuclear physics, beta decay is when an atomic nucleus emits a beta particle, a high energy, high speed electron or positron, which transforms it into an isobar of that nuclide. In this case, the reason that the mother and daughter nuclei are always isobars is because in this process, either a neutron is converted to a proton or a proton is converted to a neutron. When a neutron decays into a proton, it emits an electron and an antineutrino. That's one such example. Let's explore this even further by looking at protons more and something that is known as positron emission. When a proton undergoes beta decay, a positron and a neutrino are emitted, and the proton becomes a neutron. As we mentioned earlier, it is the emitted neutrino that we are curious about. But how exactly was the neutrino officially discovered? The term neutrino was popularized around 1934 by the father of the world's first nuclear reactor, Enrico Fermi. It has a few key properties that helped lead to its name. Its lack of charge and its tiny, tiny size are two such examples. To encase this, the word neutrino was selected. In Italian, it means little neutral one. Fermi would then propose a theory, which included Wolfgang Pauli's then still hypothesized particle. This was the first theory of one of the four fundamental forces known as the weak force. It would not be until over 20 years later, though, that we gained our first experimental evidence of neutrons. The year was 1956. Project Poltergeist was being led by two Los Alamos National Laboratory physicists, Frederick Rines and Clyde Cohen. Now, a neutrino can be viewed as a ghostly particle, flitting through matter without really leaving much of a trace. As you might be thinking, this would make it very hard to detect. To overcome this, the scientists used a fission nuclear reactor as part of their test, because such a reactor is an incredibly dense source of neutrons. So, if it's hard to pick something up, generate as much of it as you can for when you're trying. This gave them a lot of opportunities to detect neutrinos. Next to this, they placed a 10-ton detector. Now, I was curious, so for some perspective, the average weight of a car is 1.5 tons. So this detector was like 6 to 7 cars, which is pretty big, I would say. With this, and for 5 months, they collected data before this yielded the result that they were looking for. In a telegram to Wolfgang Pauli, they wrote, "We are happy to inform you that we have definitely detected neutrons." And with this, Pauli was proved correct, and the law of conservation of energy was saved. But our story does not end here, because we now have proof of a whole new particle to explore. When going into this video, I was aware of neutrinos, but I had no idea how complex they really are. So while I will be doing my best to cover them here, the chance always exists for me to get something wrong, in which case perhaps someone more educated can correct me in the comments, and we will all learn something new. With that being said, let us continue. Now, as mentioned earlier, a defining feature of the neutrino is how small it is. The rest mass of a neutrino is less than any of the other known elementary particles like quarks and bosons. The only exception to this is the photon, as it really is massless. Along with this, they have no charge, making them electrically neutral. Because of this, at least partly anyway, neutrinos do not interact with much at all. We can rule out electromagnetic forces because we know that they're neutral. They also do not interact with the strong force, the strong nuclear force, ruling out 2 of the fundamental forces. They do interact with the weak force and gravity, but on that second one, only to a small amount. Because of this, neutrinos typically pass through normal matter undetected and unimpeded. The weak force is the mechanism of interaction between subatomic particles. It is the cause of something we covered earlier in the video, the radioactive decay of atoms. Our example being beta decay. It is decay like this that leads to the creation of neutrinos. They are fermions, which means they have a half-integer spin. In physics, spin seems rather complicated to me, but in the simplest terms I could find, it is an intrinsic form of angular momentum carried by elementary particles. So, like an idea I had, and again, this is just the best interpretation of it I could come up with, but let's say in the process of beta decay, of all of the particles emitted, there is a total amount of spin that must be conserved during the decay process. And so that might have been how Wolfgang Pauli knew that the particle that was missing for them, the neutrino, needed to have 1/2 spin, because that's what would make things balance out on either side. So again, that's just one interpretation that I had of maybe how to explain this. There are also leptons, which are colorless fermions. So, man, now we have spin and color. Yeah, it's pretty crazy. Color change relates to how quarks and gluons interact through the strong force, which we know the neutrinos don't interact with the strong force. So I guess colorless makes sense. They don't have whatever it is that causes those interactions to happen. And so this is why they are unable to interact with gluons and the nuclear force. Neutrinos also come in what are known as 3 different flavors. Hey man, how's it going? I know it's later than usual. Oh, what are you doing here, man? You're sure right. It's later than usual. I'm trying to relax. I got something here on this spoon that I would really like for you to try. You want me to try something? Well, this can't be good. Okay, so here we go. I'm just gonna hand this over here. Alright, okay, yeah. You know what? Just give it here. Alright. Now, what exactly is this that you would like me to try? There's neutrinos. And I was reading the script briefing for this video earlier, and I saw that neutrinos have flavors. And so I want you to taste test them for me and then tell me what flavor they are. Yeah, you know that's not how it works, right? What do you mean that's not how it works? Yeah, flavor for neutrinos, it's not like flavor for your breakfast cereal. It's different. They're talking about a different kind of flavor. What are you talking about? Yeah, neutrinos don't interact with matter. Neutrinos don't interact with matter, huh? There's no way they'd sit on a plastic spoon. And they certainly wouldn't sit on your taste buds or my taste buds. So it's not something we can taste. There's no way they'd ever be on a spoon. Nor our taste buds. These 3 flavors are the electron neutrino, muon neutrino, and tau neutrino. Each one is associated with its corresponding charged lepton, the electron, the muon, and the tau. What a neutrino ends up as seems to relate to its mass. We now know that there are 3 discrete neutrino masses. The flavor state of a neutrino is a linear combination of these 3 masses. Something else that's interesting is a neutrino can change between flavors as it travels. This is something that we will come back to in a bit. Let's cover some known sources of neutrinos first. We already know that they can come from nuclear reactors via their radioactive decay, but where else might emit neutrinos? Some examples include black holes, blazars, and quasars, so like these really super intense high energy astronomical phenomena. There are even some primordial neutrinos that originated from the Big Bang. Another example is from supernova deep in space. In 1987, a star exploded in the Large Magellanic Cloud, a small nearby galaxy to us. This supernova, known as SN-1987A, emitted neutrinos. Here on Earth, detectors around the world picked up a small number of these neutrinos. While each detector only picked up a handful, it was still well above the normal background levels. And when you consider how weakly they interact in general, they being the neutrinos, this indicated a huge burst of neutrinos had been produced as the core of the star collapsed. So if a dying star can produce neutrinos, what about one that is still alive? For this, we can come back much closer to home and look at our sun, and even closer, an experiment in South Dakota in the Homestake Mine. Physicists John Bacall and Ray Davis Jr. built an experiment deep in this mine. Its purpose was to detect neutrinos coming from the core of our sun. An issue came up from this experiment, though. Of the number of neutrinos, like the total number of neutrinos that was expected to come from the sun, the detector was only picking up about 1/3 of that number. And this result was confirmed by experiments in other parts of the world as well. So, not just this experiment, but multiple experiments were observing that only about 1/3 of the expected neutrinos were being picked up from the sun. So, something was off. Could it be all of our detectors, or at least all the ones that were used, or our understanding of the sun, which led to the projected numbers, or could it be something else? This brings us back to those neutrino flavors we mentioned earlier, and the weird behavior neutrinos can exhibit by switching between them as they travel. Nuclear reactions in the sun should only produce electron neutrinos. So that is what the experiments were set up to detect. Yet we were only getting 1/3 the expected amount of electron neutrinos. Suppose, though, that if during the neutrino's 150 million kilometer trip from the sun to us here on Earth, they could change to either muon or tau neutrinos. Then the experiments would not be able to pick them up. This has come to be known as neutrino oscillation. When they travel, their mass can change, which means that they can transition between the three flavors as they do so. From a quantum physics perspective, this is possible because the quantum states of all three types of neutrinos can be superimposed on top of one another. In 2001, this oscillation would be proven by observations made by the Sudbury Neutrino Observatory in Ontario, Canada. The science around neutrinos is still ongoing. For example, while scientists now know that they have mass, they are not currently able to determine the exact mass of each of the different types of neutrinos. The closest we currently are, as far as I could tell, is being able to tell the mass values between them. And to even get that, I think we have to scale up the suspected masses each neutrino might have. This means that there is still a lot more about neutrinos for us to learn and discover. As we head into the future for this field of study, we are also seeing new and innovative detectors and methods. One such example being the Ice Cube Observatory, which uses a cubic kilometer of naturally formed ice to help with the process of detecting neutrinos. The LHC, or Large Hadron Collider, is also now set up to be able to detect neutrinos, and can use those instruments in conjunction with their other experiments. It is really impressive to me that in a span of around 100 years, science has come so far in understanding neutrinos, and I really am curious to see what discoveries about them might come next. I hope you all enjoyed this. If you did, maybe like and subscribe. I really would appreciate it. And if you want to see more of me, check out some of my other videos. I'll link one up here. I have one about the life cycle of a star that kind of ties into Supernova, so maybe I'll link that one. Or Google will put one there, something like that. And I hope you have an excellent rest of your day. And of course, let us all step outside tonight and look towards the stars.